Well, happy Tuesday evening. Here we are for an amateur radio extra class course, a licensing class, teaching information that you need to pass your upgrade test to upgrade from the general class up to the amateur extra class. Your instructor this evening, Gary, ham radio call sign Whiskey 4 Echo Echo Yankee, and we're going to conclude Chapter 9 this evening, dealing with antennas and feed lines. And when I talk about the chapter, I always like to show the book. This is at the American Radio Relay League Extra Class License Manual for the 13th edition. It has the current question pool in it, and so that's the book that we use. You can read a chapter in the book if you're watching on YouTube, and then watch a video, and hopefully things will come clear. That's our hope anyway. So let me show you. We had Hurricane Helene come through the upstate of South Carolina, and normally we would be finishing up the class right about now, except that put us 3 weeks behind. So if you come to the laptop, here's our current schedule. So today is December the 17th. We'll do part 2 of Chapter 9. Then we're going to take a break, everybody, for Christmas and the holidays. And many of you already have your tests scheduled, and you'll be ready. You can do it. Just a little extra reading on your part. But please come back and join us in January. Dave will have an absolutely wonderful presentation on propagation, and then I'll do a mediocre one on safety the following week, plus some practice tests. So for those of you who haven't tested, it gives you a chance to go over some of the test questions and answers and ask any last-minute questions that you might have. You do have your tests scheduled already, right? If not, here's some resources where you can find test sessions. The top URL there is for the American Radio Relay League, and the bottom is hamstudy.org/sessions, where you can find online and in-person test sessions. The finish line is coming quickly, so just hang in there. We're going to make it. So come back to me for just a sec, Bruce. Normally I have remote control for the switcher so I can kind of take control. It's not working tonight. Oh, okay. I wanted to just point out that Dave has this issue and I have this issue that goes by different names, but a knowledge bias where we know something, so we sometimes assume that you know something. And so we will just kind of jump into topics that we think have been previously explained. The other thing is that for the extra class especially, many people have gotten here by different routes. Maybe you took my technician class, maybe you took our general class and then got into the extra class. So you will have seen a lot of this stuff already. But some people just, study on their own, get their technician, get their general, and then join us for extra class. And so we use some terms and whatnot that people go, what's he talking about? And they can be simple terms. So not to worry about that whatsoever. So one thing is the relationship between frequency and wavelength. And this is what we call the pyramid, the frequency pyramid. And it's the relationship is governed by the speed of light. That's what speed is all about. And frequency and wavelength. And wavelength is how far a radio wave will travel in meters for one complete cycle of that radio wave. So speed, frequency, and wavelength. And back in the day, radios didn't have frequency markings. They had wavelength markings. Now that predates me, and I'm old. So this is the relationship and the speed of light. So we work in scientific notation and scientific the International System of Units, so the metric system. So the speed of light is 300 million meters per second. And if we take a shortcut and have the frequency in megahertz, then we can just say 300 is the top number, and the frequency in megahertz is on the left, and the wavelength in meters is on the right. So this is the relationship. And so if you want to know what is the full wavelength of a radio frequency signal and you know its frequency, you can take 300 divide by the frequency in megahertz, and you'll get the answer in meters. And we talk about the amateur radio bands, the 20-meter band, the 40-meter band. Those are approximations. This will give you the exact wavelength, which is good because I say that frequency is where we tune our radios. Wavelength has to do with how big we build our antennas. And as we read in the chapter this week, the Smith chart, they talk about transmission lines and lengths in fractions of a wavelength. That's not going to be a fixed number. It all depends on the frequency that's involved. So it's a little convoluted, but hopefully this clarifies a little bit about that. And then just some simple, which I'm not denigrating anyone, but the open circuit is on the right here on the diagram. That's when a wire falls off, and so we don't get our light bulb lit. So that's what we would call an open circuit. On the left is the closed circuit, a normally operating circuit. And then a short circuit is actually, it's a circuit that has an additional wire or something's fallen in there, or something is shorting out on a printed circuit board, and power is bypassing where you want it to go. Now, this is accidental I'm talking about here, but you can also do it purposefully. And so, come on back to me for a second, Bruce, with the camera. We'll talk more about this here in a second. Whoops, gotta get my... But here, for example, is a section of coax. You're going to see me in the workshop with this. It's about 1 meter long. And here we have bared copper center conductor, and we have the shield. Right now it's an open circuit. It's an open end. But if I wrap the shield around the center conductor, then we're shorting the end. So if you were looking in the chapter and it talked about open transmission line sections and shorted sections, this is what they're talking about. And if you're purposely doing this, well, you'd probably solder this and then cover it over with tape or heat shrink tubing, something to keep the weather out. So don't want to make it puzzling, but want you to know what we're talking about. And there are no dumb questions, understand. They're just questions you don't know the answer to, and we're happy to help because that's what we're here to do. All right, so tonight we're going to go through sections 9.3, 9.5, 2 big sections. We will be exhausted. I'll be exhausted. We'll take our 5-minute break, and then we'll come back and complete the last section, 9.5. So let's go ahead and get started with antenna systems, section 9.3. And I just want to give you a definition here. A transmission system is everything from the transmitter's RF output all the way to the antenna is your transmission system. And it may consist of something that has gain. It may be an amplifier that's in there that has a certain amount of gain, or it may have an antenna that has directionality that gives you a certain amount of gain in one direction, or it could have components that have loss. There could be a filter that's in there that has an insertion loss, or you could have transmission line. All of those things are involved in the transmission system, and we'll talk about measuring signals going through the system as we go forward. Also, one of the things that we're really bugged about, or we work on, is impedance matching. And the reason we want to make sure that system impedances match from section to section is to attain the maximum transfer of power. That occurs when you match impedances. And there are different ways that you can do it with lumped constants, the inductor and the capacitor you see here. This is an L network that's capable of doing some impedance matching. You can use an RF transformer. It's a small one up top there, but you can make them big ones for transmitting as well. And then also transmission line transformers. Quarter wavelength sections of line. Oh, there's that wavelength again. So it's based around a frequency. Remember, 300 divided by the frequency in megahertz give you a full wavelength, and then a quarter of that is a quarter wavelength. That's a transmission line transformer. We'll talk some more about these. The whole point, though, is to get a matched impedance, where, for example, a transmitter on the left is sending this burst of energy to the antenna system on the right, and all of the energy is being absorbed by the antenna and being radiated as energy. Yeah, that's what we want. That's what we're striving for. Now, worst case is 100% reflected power. This would be an open circuit where there's no connection at all. It's broken between your transmission line and the antenna. And in this case, all of the power that you are sending out to the load is being reflected back to the transmitter. So this is 100% reflected power. Now, in our day-to-day activities in amateur radio, we're not likely to have perfect match, and we're not likely to have this open circuit, but rather we'll maybe have a partial reflection, where most of the power is being absorbed by the load, by the antenna, and being radiated out into space, but some of it is coming back. Notice that in this case, the energy that is coming back has changed polarity. That has to do with the impedances of the transmission line and the impedance of the load. In this case, the load is slightly lower in impedance than the transmission line. That means that the phase will invert. These are kind of advanced concepts you don't need to specifically know about, but they're interesting, and I want you to know about them. Again, we looked at the open circuit where we had 100% power coming back. The same thing exists if we have a short circuit, where the center conductor and braid are connected together. If that were to happen by accident, for example, then all of the power that is sent out to the load is going to be reflected back. Notice its polarity shifted, but same thing. So that would be a very bad situation. That's something we would try to avoid. When you have power being reflected from a load, in that case of the partial reflection, then we have what are known as standing waves, or voltage standing waves. So the source here is on the left, and it's sending a wave, the blue, from the left to the right, and the load is accepting some of it, but sending most of it, or a lot of it, back, and that's the red that is going from the right to the left. And notice where they coincide. Let's say here, for example, there's a positive peak, negative peak, positive peak. They add together, and this is what is known as a standing wave. It doesn't move or doesn't travel on the transmission line. It just stands there and goes up and down and up and down. This is a voltage maximum right here. There's positive maximum, negative maximum. Note here, at this point, there's no voltage at all. It's down to zero and stays at zero. Oh, also notice that this is on a peak. This is a quarter of a wavelength. Oh, quarter wavelength. Where have we heard that before? We'll talk more about that. But remember, the whole point is to get the maximum transfer of power by using some form of impedance matching. And sometimes the impedance matching happens right at the antenna. And to learn more about this, we have to learn our ABCs. Well, no, they wouldn't make it that easy. Greek. We have to learn some Greek. So let's see how we can do here. This is the Greek letter delta. And one kind of antenna impedance matching is called the delta match. And it's for use with balanced transmission line. In this case, they're showing, I think, 600 ohm line. And it's high impedance feed line to a low impedance antenna. And what you do is you come toward the antenna, and then this antenna is a half wavelength long. So it's a half wavelength dipole. It's connected at the center. It's not separated. But you actually bring the wires out to points certain distances away from the center, and this will match the transmission line, in this case the 600 ohm line, to the 73 ohm impedance at the center of a dipole antenna, or so you're actually going off the center, so it's going to be matched to 600 ohms. This is a delta match. And so here's a delta fed dipole here using 300 ohm feed line. And some of the component calculations that go on. This is a delta match. Notice it's the Greek letter delta, but it's upside down. All right, next, gamma. The Greek letter gamma. This is an unbalanced to balanced connection. So again, we have a half-wave dipole antenna here, fully connected. It's not separated in the middle. The center, this is fed by coax in this case, so the center coax shield is connected right at the center. And then the center conductor goes through a capacitor and then a line that acts as an inductor and another inductor, so that schematically it looks something like this. So a gamma matched is an unbalanced to balanced connection. And it steps up the impedance from 50 ohms up to match the antenna. It has a grounded driven element, so this could be connected right to the boom of a Yagi, for example, right directly to ground, and it's no problem. And the capacitance here, this right here, cancels the inductance of the matching network. So this is a gamma match being used, let's say, for a Yagi antenna, which is a common thing. People ask me, well, Gary, I've heard of hams using their towers themselves as antennas. Yeah, you can do it for the low bands for 160 meters and 80 meters. And again, we use the gamma match. What you do is you feed it with coax. You have a capacitor. Normally this will be a vacuum capacitor, maybe a variable capacitor. You have a line that runs parallel up to the tower, up to a certain point. It doesn't have to be the top. It could be, or it could be some point in between. And if you can have a variable capacitor here, you can adjust it so that you get a 50 ohm match. Again, schematically, it looks like this. This is also called shunt feeding a tower. So the gamma match can be used for both dipoles, like for a Yagi antenna, or to gamma match your tower. If you want to know more and see somebody do it, Steve, let me get his call sign right, VE6WZ has some wonderful videos up on YouTube, and here's a URL link at the bottom where you can see him actually be doing this, and it's fascinating. Omega. Yeah, they have an omega match as well. And what an omega match is, it adds an L network in addition to some of the other matching to match low impedance antennas. And so just know that an omega match has this additional L network ahead of it. And so here's a comparison. The delta match, which kind of looks like the Greek letter delta, only upside down. The gamma match, which is that series capacitor with the bar going out and up. These are inductive elements, actually. And then we have the omega, which has this L network here in addition to the matching. And we saw the delta. And then there's a T, which is it's two gamma matching sections at the same time. We didn't talk about that. So these are different ways that you can match the impedance, the characteristic impedance of your transmission line to your antenna. The goal to get the maximum transfer of power and the minimum amount of power reflected back from the antenna. In Voice of America, we used a lot of open wire transmission lines because we've talked about it here. It's the most efficient. Standing wave reflected power doesn't bother it. You don't have the losses that you do in coaxial cable. And what we used to do all the time was if we had an antenna that was slightly out of tune, out of resonance on a frequency that we wanted to transmit on, we would retune the antenna by adding stubs to the transmission line. And stubs are just additional wires connected to the transmission line of a certain length, and they can be shorted or open at the end, either. And it's optimum to match at one frequency. And you can have dual stubs as well if you have a complex situation. Stub matching involves open or shorted transmission line added at a point along the main transmission line in order to get an impedance match. And well, where do I put the stub? Well, there's different ways that you can determine that, and I'll show you a practical one here in a little bit. But the Smith chart, if you look at the outer ring, it says in fractions of wavelength on the transmission line. The Smith chart can help you calculate where these stubs should be. Now, if you're on VHF and UHF, here's a trick. If you've built an antenna for it, but you're not sure how best to tune it up, you can do something called universal stub matching. By just, when you're feeding the half-wave dipole here, for example, you can do this with coax, and you just bring lines down from the antenna, and then you have the coax connected to these lines, and you just move this connection up or down until you get minimum SWR. And that will be a match. You can do this at VHF and UHF because the sizes of the antennas are not that big, so this is practical. You can have an open stub, or you can have a shorted stub. Both will work. Just moving the feed line up and down until you find a match, clamp it down or solder it, and boom, you're in business. That's universal stub matching. So some Yagi antennas, we've talked about half-wave dipoles that are connected all the way through so far when we talked about the gamma match, for example. But some manufacturers will actually mount their driven element for a Yagi antenna on insulators. They'll insulate the half-wave dipole from the boom. And by doing that, and if they make the dipole just slightly shorter than resonance, it makes the antenna, we say, capacitive. Remember that from last week? Because of the phasing relationship between voltage and current on that antenna. And the capacitance of the shorter dipole that's insulated from the boom can be compensated by an inductance. And the inductance looks like a hairpin. So here is a hairpin match. It's just a piece of wire. So this is the driven element here, but also in parallel with the coax, you have this inductor. Well, Gary, that's a short circuit. It is a short circuit at DC. But at radio frequencies, it acts as an inductance, and it cancels the capacitance from the shortened dipole, the half-wave dipole at the center. So this is one way that the manufacturers will impedance match the center conductor of a Yagi, for example. So I told you that everything coming from your transmitter all the way out to the antenna is your transmission system. And when you factor in all of the gains and the losses of that system, you come up with something called effective radiated power, ERP. A lot of broadcast stations are licensed based on ERP. Hams are not. Hams, the maximum output power that we can put out is 1500 watts PEP from our amplifiers. But if we have an antenna with further gain, well, we can go even higher than that. So, but knowing that we have all of these things in the system, we can factor them in, and there's some problems that they give us here to work out. Also note that the power ratio formula is 10 times log to the base 10 of one power over another power, if you're comparing one power to another power, and the answer will be in dB. So this is the formula, but you don't have to know the formula to work out these problems. So let's look at one of the problems. So the question is, what is the effective radiated power relative to a dipole of a repeater station with 200 watts transmitter power, 4 dB of feed line loss, 3.2 dB of duplexer loss, 0.8 dB of a circulator loss, and then a 10 dB D antenna gain. We'll just ignore the D part. So we've got 200 watts to start, minus 4, minus 3.2, minus 0.8, so that's a total of minus 8, plus 10, so the sum is plus 2 dB. Now, if you had been in some of our earlier classes, we make you remember that 3 dB is times 2, 6 dB is times 4, 10 dB is times 10. And with those numbers in mind, you can pretty much factor out 1 dB is the equivalent of about 1.26, 26%. So here we said that we have a gain of 2 dB, an overall gain of 2 dB. Well, one way that you can look at that is 1.26 times 1.26 gives you 1.59. So we can take that 200 watts out of the transmitter and multiply it by 1.59. And one of our students, Orlando, gave me this chart, just might help you to consider things where 1 dB, 3 dB, 6 dBs, or if you're into powers you can raise the 1.26 to the first power, second power, third power to get the various levels. So the answer in this case is 200 watts times 1.58 gives you 317 watts effective radiated power. So you started with 200 watts out from the transmitter. You had all those losses from the circulator and the transmission line, etc., and you had a 10 dB antenna gain. So overall, from the antenna in the major direction, you have an effective radiated power of 317 watts. Yeah, they wouldn't leave it at 1. There's another one. So now we're asked the effective radiated power of a station with 200 watts, 4 dB feed line loss, 3.2 duplexer loss. This looks a lot like the last problem, doesn't it? Oh, this is the last problem. This is just another way. Oh, what I was going for here is you could also approximate. It's going to be more than 200 watts that you started out, but it's not going to be 3 dB, because that would be times 2, so it's going to be between 200 and 400. Yes, again, this is the same problem, 317 watts. Okay, there is another one here. What is the effective radiated power relative to a dipole of a repeater station with now 150 watts out, 2 dB feed line loss, 2.2 dB duplexer loss, and 7 dB antenna gain? Just ignore the dBd or dBi. They're meaningless in this context. So, so we got loss, loss, gain. And we factor that all in, we have 2.8 dB of gain. Well, that's pretty close to 3 dB. And 3 dB is times 2. So if we started out with 150 watts, it's going to be pretty darn close to 300 watts. And the answer, in fact, is 286 watts. That's the one that's closest of the answers that you're given to 300 watts. So that's the way you can do that one. And of course, they have one more. What is the isotropic radiated power of a station with 200 watts transmitter output power, 2 dB loss in the feed line, 2.8 dB loss in the duplexer, 1.2 dB loss in the circulator, and 7 dBi antenna gain. All right, the whole thing is exactly the same way we did it. That's a minus, that's a minus, that's a minus, that's a plus, and it adds up to 1 dB. And we said 1 dB is 1.26. So 200 watts times 1.26, 252 watts. That's the way that you can get to the answer. You don't need the 10 log to base 10 ratio formula to get to the right answer. Oh, answers. That must mean questions. Let's see how we do. See if you can remember. It's probably the easiest. We can go back over this. So what is the effective radiated power of a repeater station with 150 watts power output, 2 dB feed line loss, 2.2 dB duplexer loss, 7 dB antenna gain? What do you think?
Delta.
It is delta. This is the one we just did. It's very close to 3 dB. It's 2.8 dB. So 286 watts. All right, what term describing total radiated power takes into account all gains and losses?
Charlie?
Yes, and this is so FM broadcasters, this is what their license from the FCC reads. You will have a certain output power, effective radiated power from your station. And what is the effective radiated power of a repeater station with 200 watts output, 4 dB feed line loss, 3.2 dB duplexer loss, 0.8 dB circulator loss, and a 10 dB antenna gain? This was, the overall was 2 dB of gain. So we start out with 200 watts with 2 dB of gain. What's the answer?
Alpha.
200 times 1.56?
Alpha.
Yes, 317 watts. Now here, notice they're close, 300 and 317. So this is one you might have to watch for. What is the effective isotropic radiated power of a repeater station with 200 watts output, 2 dB feed line loss, 2.8 dB duplexer loss, 1.2 dB circulator loss, 7 dBi antenna gain?
Bravo.
Yeah, we said it's about a 1 dB difference, so 1.26 times 200, 252 watts. Please go back over these and review them. They'll come clear to you. It's really fairly simple math, eventually. Just understanding the concepts. So, which matching system for Yagi antennas requires the driven element to be insulated from the boom?
Hairpin.
That's the hairpin. It's also known as a beta match, but hairpin, indeed. High gain was famous for that. So what antenna matching system matches coax cable to an antenna by connecting the shield to the center of the antenna and the conductor a fraction of a wavelength to one side? What is that called?
Alpha.
It is alpha, which is a gamma match. Absolutely. This is a gamma match. And what matching system uses a short length of transmission line connected in parallel with the feed line at or near the feed point? It's what we used to do in VOA.
Delta.
It's a stub match, absolutely. And what is the purpose of the series capacitor in a gamma match?
Bravo.
Yes, it cancels unwanted inductive reactance. And what Yagi-driven element feed point impedance is required to use a beta or hairpin matching system?
Inductive.
Alpha. Alpha.
So the hairpin itself is inductive, but the driven element itself, we make it a little shorter than it normally would be to make it capacitive, so the two cancel each out. And so the answer here is capacitive. The driven element is electrically shorter than 1/2 wavelength. Then you can use the hairpin. And which of the following is used to shunt feed a grounded tower at its base?
Charlie.
That's the gamma match, another use of the gamma match. And which of the following is a common use for a Smith chart? One of them.
Alpha.
Yes, you can determine the length and position of an impedance matching stub. Very good. All right, that was a lot of stuff. But guess what? In the next section, there's even more. But we can do it. We are strong. Transmission lines. So RF ammeters you don't see them too often in amateur radio, but in commercial radio, especially commercial AM radio, most broadcast transmitters had an RF ammeter in the front panel of the transmitter or mounted on the transmission line going out to the antenna. And in fact, in the case of AM broadcast, their license, instead of using ERP, might say a certain amount of amps, 10 amps of RF current to the antenna system. So in ham radio, we can still do that. We can use an RF ammeter. Here's an MFJ model. Long live MFJ. It may be obvious, but more current equals more power. So if you were rated to be able to transmit at 10 amps into an antenna array, but you were only transmitting 8, well, that's less than your rated power. So more current equals more power. All right, most of the time we don't analyze our antenna systems using an RF ammeter. What we typically do use are these handheld antenna analyzers. Here's one from Rig Expert, but a bunch of other folks make them as well. An antenna analyzer has a built-in low-level, low-power RF source. It can measure standing wave ratio in your system. You can have it measure at a single frequency, or you can have it sweep an entire band, for example, if you're looking to see what the bandwidth of your system is. Most of them have an interface to your computers where you can then plot to a graph or a Smith chart. Many of them will have direct readout in rectangular notation of the resistance of a load plus its reactance. So you can use that in doing calculations. And one other nice thing about these antenna analyzers is they're battery operated and they're portable. So you can easily carry them to the base of an antenna or use them up on a tower. Also, many analyzers have these capabilities. Measuring a transmission line cable or a coaxial cable's velocity factor. We'll talk more about that, but that has to do with how fast radio frequency energy can travel through the cable. It's actually not at the speed of light, it's reduced. But also something called a time domain reflectometer, TDR. It's a function to measure cable lengths. So let's say you have a cable, but you don't know how long it is. You may be able to connect it to your antenna analyzer, put it in the TDR function, leave the far end open, and it'll tell you, if you know the velocity factor of the cable, it'll tell you how long that cable is, 132 feet, for example. Cool. And you can also use it to determine the resonant frequency of a circuit, kind of like a grid dip oscillator used to be used. So, notice there are 3 answers here. That might give you a clue, but these are some of the features of antenna analyzers. And they can measure, as we said, the standing wave matching of an antenna transmission line system. Another thing that can be used to do that are directional power meters. You'll see these at ham fests. Bird and others made these. They have slugs. That's this device right here. See, there's ones being stored in a little storage area over here. These are made for certain frequency and power ranges. So the enclosure is just a meter. It's a meter inside of an enclosure. This is where the magic happens. And it has what I call a goes-in-a on one side and a goes-out-a on the other side. You feed your transmitter signal in through there, and this goes out to the load. And with the slug, with the arrow pointed in this direction, you can read the amount of power that is going out to the load. And if you take this slug and rotate it 180 degrees so the arrow faces the other way, then you can read the reflected power that is coming back from the load. And when you have those figures, you can know that if you have the forward power of 100 watts, reflected power of 25 watts, well, then the power absorbed by the load is 75 watts. That's one thing you can know. And there's also a chart on the back of most of these meters where you can plug in these numbers and you can calculate the standing wave ratio. So this requires a transmitter. It's not as portable, but it is another way where you can measure power and calculate standing wave ratio. And the hookup, as I mentioned, for the directional watt meter, you have a transmitter sending power out to an antenna. Whereas here's an MFJ antenna analyzer. This just connects directly to your transmission line and out to your antenna. This is a test load right here, a dummy load. But antenna analyzers connect directly to the load. All right, you had to be really well heeled a number of years ago to even get your hands on one of these or work at a very well-endowed university laboratory. This is a network analyzer, one of the original ones. This is an HP. And connected down below the network, this is the network analyzer here, and connected down below by these cables here is known as an S parameter test set. And with this device and a circuit that you had known as the device under test, you could calculate and measure certain characteristics of that device. This guy was unbelievably expensive, $20,000 I'm guessing. Well, hams didn't have the access to this until certain hams were innovative, and one was a German ham, DG8SAQ, who came out with this, the VNWA3, which has everything in one box here. The S parameter test set is built in here and had a single port here and another port here, and it could characterize components up to 1.3 gigahertz. It used software that was on the PC. We had an internal RF generator and low noise analyzer. It would measure S parameters. It would do SWR plots. It had a Smith chart display. Really nice unit, but then that was superseded by another innovation from, I believe, a Dutch ham who designed the circuit originally, and the Nano VNA, which list price was $94 on Amazon, but during Black Friday they had them on sale for half price. So you could buy one of the Nano VNAs for about 56 bucks. These will work from 10 kilohertz to 3 gigahertz. They're compact and powerful and will give you a lot of the same information that you would have gotten from that $20,000 HP network analyzer. Of course, not to the precision and accuracy, but for amateur radio use, it's generally just fine. Now, only recently did I come across this, which I think is going to be one of the best finds of this class for you. This book, Nano VNAs Explained. And it's available in two ways. There's a Kindle version that you can get from Amazon, and it's $18. Or you can get the original printed version from the Radio Society of Great Britain. This is an RSGB book, and it's about 15 pounds, but I don't know what the shipping to the United States is. But it's 112 pages. This is the missing instruction book to know how to use a Nano VNA. And it doesn't have to be any particular Nano VNA because they all work very similarly. And they have two ports, generally, one with both a send and receive capability, and the other that just has a receive capability. This port is able to measure voltage and phase of signals. So this is a single port VNA would be here. It consists of mixers that actually take it down to an audio level, and the audio then represents the measurements that are made. It's a very, very clever design and very innovative. No matter whether you're using that $20,000 unit or the German one or this one, you really want to do a calibration before you use the VNA. And you do that, there's a procedure that the book will talk about, but it's pretty self-explanatory in the menus, where you connect three different things. An open circuit connection where there's nothing there except a shell of a connector, a short circuit, the center conductor connected to the shield, and a 50 ohm load, because that's what we want to normalize the VNA to 50 ohms. And after you've done the calibration procedure, you then are ready to go. The interesting thing is that the calibration procedure doesn't have to happen right at the unit. So here's the top is the test port where you would do this. But if you've got, for example, your transmission line going out to your antenna, if you do the calibration out here by your antenna, then all of this transmission line is factored in, and you don't have to know. All you'll see are the characteristics of what's going on at the antenna. And well, what can the VNA tell us? Well, it can tell us the input impedance of the antenna, for example, or an output impedance of a filter or something like that, and the reflection coefficient. And reflection coefficient is analogous to voltage standing wave ratio. It's just another way of characterizing that. I'll show you a table here in just a second. Here's one of the diagrams that's in the book that kind of shows you some of the things that can be measured using the VNA here with a low-pass filter. Well, let's do it. Let's go down to the workshop. We're going to have audio from the laptop there, Bruce. Let's see what I can do. I want to demonstrate the use of the nano VNA to measure the output of this filter. It's a trap, and we're going to see if we can determine approximately what frequency range it is. We've already calibrated the VNA using the three loads, the open, the short, and a 50 ohm load. And right now we're sweeping between 150 megahertz to about 300 megahertz. And the output of the nano VNA is on the top. We're going to run that into one side of the filter. And then the other side of the filter we'll bring in down here. See if I can get it on there. And there you can see that the response has got a nice definite notch there. Whoops, and if we go over with our marker, we can see that the marker frequency is about 189 megahertz, which pretty much corresponds to what I measured earlier, around 185 to 190. So this is using a nano VNA to measure a filter response. In this case, a notch filter. So my audio garbled there at the very end, but a notch filter is what we were looking at there. Came from Europe and was used to notch out some interference from a TV circuit, actually. The VNA will give us information known as S parameters. Remember, I showed you that box underneath the Hewlett-Packard network analyzer, the S parameter test set. So S parameters come from optics, but also radio waves can also be characterized using these same things. And so they're known as scattering parameters. That's what S parameters is. And you can characterize gain, return loss, VSWR, the reflection coefficient, stability, all sorts of different things using these S parameters. And it's the S and then numbers indicate the ports where the signal can enter or leave a device under test. So you need to know two. So S21 is the forward voltage gain, or the forward gain of a filter. Well, most filters don't have gain, but you can see the pattern of the filter, for example. That's forward gain or loss. So S21. Also, if you had an active device that did have gain, you could measure that as well. And then S11. S11 is the voltage reflection coefficient, also known as return loss or reflection coefficient. So returns. Here's desk ESC11. He's returning something. So these are the two you want to know. S21, forward gain. S11, return loss. And you measure those here, for example, S21, you're using a 2 ports. Here's the device under test going back in. S11, you're using just a single port. And S11, we're looking at return loss. S21, forward gain. So reflection coefficient, I mentioned it's analogous to standing wave ratio, and actually it can be derived from the standing wave ratio. It's SWR minus 1 over SWR plus 1. You can bring that up at your next party, whatever. People will be fascinated. Okay, maybe not. Engineers use return loss and reflection coefficients. Hams typically use VSWR, but we're talking about the same thing. We're talking about the reflected signal coming from an impedance mismatch at a load. And so it may be kind of hard to see on the screen here, but if you look in the handout with the PDF that we'll make available to you at the Dropbox link, you can find it in the description box on YouTube. It'll have this chart, and you can see return loss, reflection coefficient, and standing wave ratio. So a return loss of 1 dB is not real good. It's a VSWR of 17 to 1. Ugh, that's not good. Whereas if we get to a VSWR of 1.02, well, that's a return loss of over 40 dB. That means that the signal coming back from a load is 40 dB less than what was sent out. That's a good match. And the reflection coefficient is another way to characterize that as well. So impedance matching, remember the goal to get the maximum transfer of power. Well, one of the ways that you can impedance match is using a quarter wavelength long section of transmission line of a certain impedance. So let's look at this situation. We have here, we're coming in at 50 ohms, typical from a transmitter, and our load, might be an antenna or something like that, has an impedance of 100 ohms. Well, one way that we can impedance match this is by getting a transmission line, coax, something like that, that is midway between these two. So there's 100, there's 50, midway between would be 75 ohms. And this section would be a quarter wavelength long at the frequency that you want the impedance match to be at. And it will also take into account the velocity factor of the transmission line. We'll talk more about that coming up. But this is known as a transmission line transformer. And it's really a very practical thing to know about and to be able to use. In my case, I'm in charge of the VHF-UHF station for our field day operations. And this coming June, I'm going to jazz it up a little bit. Normally we've just had a 2-element Yagi for 6 meters. 6 meters is the money band. That's where we make all of our contacts. And you're limited to the amount of output power that you can have. 100 watts is as far as we can go. Well, what could I do? Well, I could put up a bigger antenna, except then you have to put up a bigger mast, and it gets a problem. So what I have worked out is that I'm going to put an array out at field day, 2 over 2. 2-element Yagi over another 2-element Yagi. This is what I do here at my home station. And it'll give me at least 3 dB of gains because I've got a second antenna. And the two working together will give me a lower angle of radiation, which should give us a stronger signal at distant locations. Okay, and so problem is when the top antenna is a 50 ohm antenna, the bottom antenna is a 50 ohm antenna, and when we connect them together in parallel, well, then we have a 25 ohm antenna. And so I need to come up with a way to match. And so take my picture off of there, Bruce, just for a second so they can see. Yeah, okay, so here we go. Here's 50 ohms coming from the transmitter. Here's our 25 ohms, two antennas in parallel. What I need to do is to have a quarter wavelength long line here at 37.5 ohms. So you can select a cable impedance midway between the two. Well, how am I going to accomplish this? Well, I'm going to accomplish this through one of two ways. So there's a commercial product, a combiner splitter. This is one made by antennas-amplifiers.com. I believe they're in Serbia, but I can't remember. The URL is there. You can go take a look. Well, this looks like a convenient way until when you walk over here, come on over to the green screen. So 6 meters, all right? 6 meters is the full wavelength of the signal. 3 meters would be a half wavelength. 1.5 meters is a quarter wavelength. Here's a meter stick, 1 meter long. Here's the antenna amplifier's coupler. It's got two connections for the antennas at one end. It'll go way down at the bottom. There's another connection there for the transmitter. This is 1.5 meters long. It's a quarter wavelength long. And inside, I know I've opened it up, is a copper tube through an air. There's no other dielectric material in there, so it's through air against the case here. And so this is a way that we can transform my parallel antennas, 25 ohms, back to 50 ohms using this. And so I did use the vector network analyzer to characterize it. You only need to look up here. This is for gain. But so on a Smith chart, this is the match we have here, and here's the return loss, the VSWR graph. Hey, not bad. But that was, a commercial product, and I thought, I wonder if I could build one myself. Well, okay, I'm probably not going to be able to construct the nice transmission line. That, by the way, that unit is rated at full legal power, 1,500 watts, I think it is. So I'm probably not going to do that, but could I do it on my own for a lower power? And the answer is yes. So come on back over here. What you can do is, if you've got coaxial cable, that is, in my case, this is RG6, which is 75 ohm cable. If you put two of them in parallel, the combined impedance is half, or 37.5, close enough. And so this is my homebrew. It's got two connections here at the top, one connection here at the bottom. Now, this RG6 is not going to be full legal limit, but for 100 watts, I bet it would work just fine. And I did go ahead, whoops, I don't want this to fall off, and characterize it here on the VNA. So build my own. And you can see it looks very similar with a SWR plot on the Smith chart here and the return loss here. So the combiners, though, are using different dielectrics. As I mentioned, the antennas amplifiers uses air. Air has a velocity factor of 1. The speed of light, or speed of radio waves, is 300 million meters per second with an air dielectric. When you change the dielectric, however, to polyethylene, which is used in RG6, the velocity factor there is only 0.66. Hence, the physical lengths are different, even though their electrical lengths are the same. So my combiner is actually only, I think, 1.3 meters long, whereas the antenna's amplifiers is a full 1.5 meters long. So velocity factor is something that we need to know about. Radio travels at the speed of light in a vacuum and through air nearly as fast, but if you use insulated wire or coaxial cable, which has a plastic dielectric, that will cause a slowdown. So I'm asking, Gary, I want to put a dipole antenna up, but I want to use insulated wire. Can I do it? Yes, you can, but you will find that your antenna, when you get it all said and done, is going to be shorter than if it was uninsulated because of this velocity factor effect. So velocity factor is expressed by the velocity in the transmission line divided by the velocity of light in a vacuum. And it's always going to be 1 or less. So for an air dielectric, it's 1. For other things, it's less because, as Albert says, plastic makes waves slow down. Good thing we're not doing this calculation in 186,000 miles per second. Okay, so coax cable typically has either solid or foam dielectric. And the dielectric, the thing that we're talking about, is this white right here. And so here we have the shield, the braid, and here we have the center conductor, but it's this white area right here, the plastic dielectric. Foam dielectric is just as you talk about it. It's a foam material, has a lower safe operating voltage limits because it's not as heavy duty as polyethylene. It has a lower loss per unit of length, so okay, if you're looking for every last dB of signal, this might be a good thing. And foam dielectric has a higher velocity factor. Waves travel through it faster, closer to the 1. And the way you know whether you've got poly or whether you've got foam, a knife will very easily go through foam, whereas with polyethylene, you kind of got to work at it. So the velocity factor of foam is 0.8. The velocity factor of polyethylene, the more solid stuff, is 0.66. It slows down the velocity of the radio waves. And here's a table that tells you open wire line, for example, with an air dielectric is very close to 1. But again, foam 0.8, solid polyethylene 0.66. So in our book, let me just put this back over here, okay. They ask us, what is the approximate physical length of a solid polyethylene dielectric coaxial transmission line that is electrically 1/4 wavelength long at 14.1 megahertz? Well, let's try to solve it. So here are our questions. These are the things that we want to work out. The wavelength in meters, the quarter wavelength, then we have to calculate in with the velocity factor, and finally the total length. So the wavelength in meters for a full wavelength is going to be 300 divided by 14.1. Remember that pyramid we started out with. So that gives us 21.28 meters. That's the actual wavelength. A quarter of that is 5.32 meters. But because we travel slower in polyethylene by a 0.66 factor here, the length is going to be 0.66 times that, or 3.51 meters. And that's exactly what I had to go through when calculating for this the combiner that I showed you over there. All right, here's another one. What is the approximate physical length of a foam polyethylene foam now, a dielectric coaxial transmission line that is electrically 1/4 wavelength long at 7.2 megahertz? Well, we go through the same process. 300 divided by 7.2 will give you the full wavelength, 41.67 meters. A quarter of that is 10.42 meters. And foam has a velocity factor of 0.8, so the length is going to be about 8.3 meters. So there we've talked about polyethylene, and we've talked about foam. Air insulated line, the velocity factor is close to 1. So keep that in mind. What is the approximate physical length of an air-insulated transmission line that is electrically a half wavelength long at 14.1 megahertz? All right. 300 divided by 14.1 is 21.28. Half wavelength is going to be that times 0.5, or 10.164. If the velocity factor is 1, then we're going to be really close to 10.6, and so that is the answer to the problem, because air insulated doesn't really slow things down. Now, air insulated is probably the lowest loss. Most hams don't build their own transmission line anymore and have it air insulated. They might buy ladder line though. It's the lowest loss per 100 feet of the commercially made products, and it kind of mimics what we used at the VOA relay stations when we used open wire parallel transmission line, and it's very easy to add stub tuning. So just know about ladder line. It has the lowest loss per 100 feet, much lower than coaxial cable. So I gave you all an assignment in an email that I sent out to you, asked you to watch this video, Standing Up for Standing Waves. I hope you found it as entertaining and educational as I did. And 2 rules that I want to bring back from that: that a half wavelength line is an impedance repeater, whereas a quarter wavelength line is an impedance inverter. And what that means is that if you have an open at one end of a transmission line that's a half wavelength long, it'll be open at the other end. Or if you have a 50 ohm load at a cable that is a half wavelength long, it'll measure exactly 50 ohms at the other end. Now, a quarter wavelength line, on the other hand, is an impedance inverter. So if you have a short circuit at one end, it'll appear almost open at the other end, or if it's open at one end, it'll appear almost shorted at the other. So keep these 2 rules in mind. A half wavelength line is an impedance repeater. A quarter wavelength line is an impedance inverter. And we can see this if we take on the case of the half wave dipole. If we take a look here, here's our diagram of a half wave dipole. The red is the voltage, and the blue is the current. And remember, we talked about impedance as being the ratio between voltage and current. So when we have high current, it's going to be low impedance at the center, and a quarter of a wavelength away, it's the opposite. It's high voltage, low current. Quarter wavelength in the other direction, same thing, high voltage, low current. And so here we're looking at the low impedance point, high current, low voltage. Here's the high impedance point on the antenna, high voltage, low current. So this distance being a quarter of a wavelength goes along with the principle of a quarter wavelength wire or cable being an impedance inverter. Well, what about the in-betweens? So lengths of coax that are not a quarter wavelength or a half wavelength, there are multiples thereof. There are 2 types. You can have it open-ended or shorted, and we talked about that earlier tonight, remember, where you can have, if the ends are open. Wait, come back to me just for a second. This is open, all right, see, not connected together. This is shorted. I do have the braid and the center conductor connected together. So if you have a length of cable that is less than a quarter wavelength, for example, it will behave as a reactance. What? So this is the table 9.33, or on page 9-40. And so here's the case of open lines. So they're open at the end. And if it's an 1/8 wavelength long, it will behave as if it's a capacitor. Whereas if it's 3/8 of a wave long, it behaves as an inductor. So you can actually make components that you can use in your projects out of transmission line. I was making a 20-meter transmit loop, and I needed a capacitor for impedance matching, and I didn't have a suitably rated capacitor in my junk drawer. It was a very small capacitance, and I thought, I can make it out of coax. And I did. And it worked perfectly. So this is a practical application. There's another table with shorted lines. So in this case, instead of being a capacitor, a shorted eighth wave line is an inductor, and vice versa. A 3/8 wave line is a capacitor. So eighth wave open lines appear as a capacitance, like two plates of a capacitor. We're talking about open lines here. And a shorted line appears as an inductor, like a single turn inductor. And I wondered, I used this very piece of coaxial cable, and I wondered, well, can I prove that with my LCR meter? Let's find out. So here we are in the workshop with a 1 meter length of RG213 coaxial cable. And here I have an LCR meter, a digital LCR meter. You notice that the ends of the cable, in fact, let's zoom in just a little bit here. I just have them bared out. Whoops, where am I? There we are. So you can see. And I'm going to connect the test leads from the LCR meter to the open coaxial cable. The cable is 1 meter long. RG213, and if we noticed on the LCR meter we're on the 200 picofarad scale, this open 1 meter length of RG213 has 95 picofarads of capacitance. Well, what happens if we short the other end? Let me just reach up and do that very same thing by wrapping the braid around the center conductor tightly. Notice the capacitance went away. But if we go over to the 200 microhenry scale, we can see now that the cable is exhibiting about 1.3 microhenries of inductance. So a short cable, less than a quarter wavelength long, open is going to act as a capacitor, shorted is going to act as an inductor. So that is frequency specific, and I'm not exactly sure what frequency the LCR meter uses to make the measurement, but I knew it was going to be shorter than an eighth of a wavelength, so I was pretty safe in doing that test. Just here we have 3/8 wave open line appears as an inductance, 3/8 wave shorted line appears as a capacitance. This is just nice to know. It's not blue text. All right, moving on. Resonance circuits, we can have two flavors, a series resonance circuit and a parallel resonance circuit. And just ignore the R here, up here, but that represents losses. But here's our series resonance circuit with a capacitor in series with an inductor, okay? And here's our parallel resonance circuit with a capacitor in parallel with an inductor. And if you were to put these in line as filters in between a load, they would have the same power curve. The series circuit would be in series and would only pass energy at the resonant frequency. The parallel circuit would shunt energy to ground except at the resonant frequency. So this curve would actually look the same. And what I want to say by that is that they can be considered to be equivalent. Series resonant circuits and parallel resonant circuits have equivalency. In the series circuits, we deal with impedance, the R plus JX or R minus JX. Whereas in parallel circuits, we deal with something called admittance. And the subtexts of admittance are Z, R, and X for the series, and Y, G, and B for the admittance part. So hold that thought just for a second. All right. want to introduce the concept of nomograms. You don't find these much anymore, also known as alignment charts. But if you know two values, you can find the third just by drawing a line through the two and read the answer over here. So this is an Ohm's law nomograph. You can find it here at this URL if you'd like to take a look at it. A slide rule is a nomogram as well. It allows you to use sliding scales to do calculations, all right? So right now we come to the most important part of your amateur radio extra class, humbly speaking. It is time. Prepare yourselves, please. I am the Grand Poobah of the Smith Chart Society. It's a very secret society. Not too many people know about it. Shh. But it is my great pleasure to introduce to you the mother of all nomograms, the Smith chart. Named after this gentleman, the Philip Hagar Smith, and the Smith chart there on the right. It always reminds me of, I don't know how old you are, but the old TV series Time Tunnel. You remember this thing here? Well, Smith said that from the time I could operate a slide rule, I've been interested in graphical representations of mathematical relationships. And I think I might have covered up my microphone. I apologize for that. So here's our old friend, the Cartesian plane. Remember we talked about this when we were talking about rectangular notation of complex impedances. Let's go over to the blackboard here. So remember, there is no such thing as negative resistance. So I'm just going to omit this part of it right here. But over here is the R-axis. This is the real axis, okay? It's 0 ohms over here, and it's infinity over here. Well, what Philip Hagar Smith did, kind of cleverly, is you see these are the reactance axes, going up right here. This is inductive reactance and capacitive reactance. Well, he said, well, what if I took these and bent them around in a circle? So now the reactance marks are here on this circle. Infinity is still over here. 0 ohms is still over here. This is the basis of the Smith chart. So a basic Smith chart graphically depicts complex impedance consisting of resistance and reactance in series, as we're looking here on this Smith chart. The center line, so remember here's 0, here's infinity, this is unchanged, this is resistance. This is the real number in that complex notation. A value above the line is inductive reactance, that's up here. A value below the line is capacitive reactance, that's down here. And the outer circle is the reactance axis. He took the Cartesian and just bent it on around over. And so the markings follow this circle. So the outer circle is the reactance axis, and the straight line is the resistance axis. And we have something called resistance circles. Anything that is on this circle, for example, is going to have the same R value, the real value. Anything in this circle is going to have the same R value. It's going to have a different reactance value. And then reactance arcs. Anything along this arc is going to have the same reactance value. or anything along this arc is going to have the same reactance value. And remember, we talked about on the outer band, it talks fractions of transmission line electrical wavelength. This is used with the Smith chart calculations for transmission lines. We're not going to go in depth on the Smith chart, but I'm going to give you some resources where you can go further. So resistance circles. Oh, note here in the middle, this is known as the prime center, and on most Smith charts, it's indicated by the number 1. All right? Here's 0. Here's infinity. So the number 1 can actually be said to be any impedance that you want. So if we were going to normalize this Smith chart to be a 50 ohm Smith chart, we would say 1 is the same as 50, or 1 times 50 is 50. So that would be the 50 ohm point. 0.5, this is going to be 0.5 times 50, this would be the 25 ohm point. This would be 2 times 50, this would be the 100 ohm point. So that's called normalizing the Smith chart by setting the value of what the 1 is going to be. And again, we have an open circuit or infinity here at the right, a short circuit or 0 ohms here on the left for resistance. Above, it's R plus JX, above the line. Below the line, it's R minus JX. And then we've looked at the reactance arcs. We looked at those as well. Anywhere along this arc is the same reactance value. They're also normalized. So if it's times 1, well, that would be the 50 ohm arc. Don't have my glasses on. I don't know where I put my glasses, actually. Oh, there they are. All right, there we go. Let's see if I guessed right. Yes. All right. I talked about the prime center and normalizing a chart. That's assigning a value to the center. So we're saying the 1 is 50 ohms. That's the way most of these work. And then other points are multiplied in the same way to give the values of resistance and reactance at other points on the Smith chart. Normalizing. And you can also draw something else on the chart, standing wave ratio circles. If you take a compass and draw around the normalized center, okay, 0.5, that's going to be a 2-to-1 standing wave ratio, 25 ohms to 50 ohms, 2-to-1, or 100 ohms to 50 ohms is going to be a 2-to-1. This circle, anything within this circle is going to be an SWR under 2-to-1. So if you look at a network VNA, they may give you a display. You saw some of those before. If it's within this 2-to-1 SWR circle, you're golden. You're fine. It's a pretty good match. And again, it says wavelength toward the load, which mostly is the antenna, or towards the generator. That's the transmitter. That's on the outer ring. Useful to calculate the impedance along a transmission line. We're going to come to a break here in just a little bit, but hang in there. We're almost done. We used to stop right here, but I want to give you more of the story. As Paul Harvey used to say, here's the rest of the story. Remember, we talked about the resonant circuits. What we've discussed so far is series impedance, but remember I said there's an equivalence. There's parallel admittance as well. So think of a parallel universe, and you can have admittance curves as well. And you do that by rotating the Smith chart by 180 degrees. So you have, here's impedance, Z, and here's admittance, Y. And so we have infinity here, all right? This is infinity for the Z, and here's infinity for admittance. And, well, let's go over to the calculator cam. So here is a Smith chart like we've looked at in the book, and like I sent you an example. This is series impedance, and here's parallel impedance, and watch what happens. This is kind of miraculous. If you put them on top of each other, and if I can do this the right way, Let me see. There we go. Getting there. You have a chart that shows you both the impedance and admittance curves at the same time. And in fact, you can go to Amazon, and if you buy a book of Smith charts, it has both of these. The admittance is a little lighter in color there, but they're both there. What's that all about, Gary? Why is that important? Well, here's some more information. You can go to this URL, but the thing is that we can convert impedance to admittance through this process, this graphical process, and then we can use that admittance value to determine the parallel element, and what we can do then is actually do impedance matching using the Smith chart, using L networks. The series element is described in the impedance Smith chart and the parallel element described in the admittance chart. You cancel the load's reactance and transform the resistance to 50 ohms. That's the beauty of the Smith chart. So more than you really need to know necessarily, but I wanted to give you the full flavor of what we're talking about and the power of the Smith chart. The biggest reason for the Smith chart, in my opinion, is impedance matching. All right, so we looked at that, outer ring, and it says, length, away from the generator or toward the load. That becomes important because of standing waves. So standing waves, we looked at it before, but let's look at it again. The transmission line has a length, and along that length, these waves just stand there, and there's a high voltage point, and there's a low voltage point. And they're a quarter of a wavelength apart at the particular frequency that you're operating at. And you can actually physically determine this with open wire line using a fluorescent tube. We used to do this in VOA. You could walk the line, hold the tube up toward the line, and it would light at the high voltage point and go dark at the low voltage point, and you could use that to calculate, where you are and where stubs needed to go. So just something you probably will never do, but it can be done. And you can also then use the Smith chart in concert with that to calculate fractions of wavelength and find the high impedance and high voltage points using the Smith chart. I'm going to provide you with some additional handouts tomorrow on impedance matching and another paper. Also, I want to point you to these URLs here for YouTube videos. And if you are tired of using paper, don't want to get involved in that, but you like to use computers, let me introduce you to something called SimNec and SimSmith. Free Windows software written by Ward Harriman, AE6TY. They've got a group.io for SimSmith. And then the videos of Larry Benko, W0QE, on how to use SimSmith. It's magical, and it's very complex, and you'll be way over your head very easily, but keep going because it's fascinating. And so just want you to know about this. All right, that ends your introduction to the Smith Chart Secret Society. Let's answer some questions and take a very well-earned break. All right. So which of the following is an advantage of using an antenna analyzer compared to an SWR bridge? What do you think?
Bravo.
Yes, antenna analyzers will compute standing wave ratio and impedance automatically. They'll even give you an R plus JX display. So which of the following is used to measure SWR? Read carefully.
Delta.
Yeah, all of those in their way can be used to measure SWR. directional watt meter, vector network analyzer, or an antenna analyzer. So which of the following can be measured with an antenna analyzer? Again, read carefully.
Delta.
Yep, all of those, the velocity factor of a cable length, or the resonant frequency of a tuned circuit, all could be determined. All right, which S parameter is equivalent to forward gain?
Charlie.
Yeah, S21. And which S parameter represents input port return loss or reflection coefficient?
Alpha.
Alpha.
Yeah, S11. And what three test loads are used to calibrate an RF vector network analyzer?
Bravo.
Yes, a short circuit, an open circuit, and 50 ohms. So how much power is being absorbed by the load when a directional power meter connected between a transmitter and a load reads 100 watts forward and 25 watts reflected? $100 watts forward, 25 watts reflected. How much is being absorbed?
Delta. Delta.
75 watts, correct. And what do the subscripts of S parameters represent?
Alpha.
Yeah, it represents the port or ports at which measurements are being made. And which of the following can be measured by a two-port vector network analyzer? You saw me do it.
Bravo.
Yeah, the filter's frequency response. We found the notch. So which of the following can be measured with a vector network analyzer? Read carefully.
Delta.
Yeah. Input impedance, output impedance, reflection coefficient, all of those can be determined. And which of these transmission line impedances would be suitable for constructing a quarter wave, they call them Q sections, a transmission line transformer, for matching a 100 ohm feed point impedance to a 50 ohm transmission line? What's the rule?
Charlie.
Midway between the two, so 75 ohms. And what parameter describes the interaction of a load and transmission line?
Charlie.
And their interaction. The interaction of a load, an antenna for example, and a transmission line. How well is it matched?
Baker.
Yeah, reflection coefficient, hams we would say SWR, but yeah, the impedance mismatch is what we're looking at there.
Okay.
Not sure I love that question, but okay. What is the velocity factor of a transmission line?
Delta.
It is delta. It's always going to be 1 or less. It's the velocity of a wave in the transmission line divided by the velocity of light in a vacuum. Which of the following has the biggest effect on the velocity factor of a transmission line?
Charlie. Charlie.
Yes, the dielectric, the insulating dielectric material. And why is the electrical length of a coaxial cable longer than its physical length?
Delta.
Yeah, think of Albert Einstein with his speed meter there. Electromagnetic waves move more slowly in coaxial cable than in air. So its electrical length is going to look longer than its actual physical length. And what impedance does a half wavelength transmission line present to an RF generator when the line is shorted at the far end? Half wavelength lines are impedance.
B.
I heard B. It's shorted at the far end, which is a very low impedance or low resistance. Yes, so half wavelength lines are repeaters, impedance repeaters. So if it's low at the one end, a short circuit, it's going to be very low at the other end. And what is the approximate physical length of an air-insulated parallel conductor transmission line that is electrically a half wavelength long at 14.1 megahertz? So 14.1 is in what meter band?
20.
And half of that would be?
Charlie.
Yeah, Charlie, 10.6.
Okay.
There's no dielectric because it's air insulated, so. All right, how does parallel conductor transmission line compare to coaxial cable with a plastic dielectric?
Alpha?
Alpha. Parallel conductor transmission line has lower loss per 100 feet, much lower than coax. So which of the following is a significant difference between foam dielectric coax and solid dielectric coax cable, assuming all other parameters are the same? Read carefully.
Delta.
Foam dielectric coax cable has a lower safe maximum operating voltage because, yeah, it's got holes in there. Foam dielectric coax cable has a lower loss per unit of length, yeah. Foam dielectric cable has higher velocity, yep, all of those. So what impedance does a quarter wavelength transmission line present to an RF generator when the line is shorted at the far end? Quarter wavelength transmission lines are impedance.
Alpha.
Inverters, so alpha, very high impedance. Quarter wavelength transforms it. All right, what impedance does an eighth wavelength transmission line present when the line is shorted at the far end? What does it behave as?
Charlie.
Yes, it behaves as an inductor.
Mm.
And what impedance does an eighth wave transmission line present to an RF generator when the line is open?
Charlie.
Charlie.
It behaves as a capacitor, yeah. And what impedance does a quarter wavelength transmission line present to an RF generator when the line is open at the far end? A quarter wavelength transmission line is an impedance. Inverter. So if it's open or high impedance at one end,
Charlie.
it's going to be a very low impedance at the other end of a quarter wavelength. So keep that in mind, repeaters and inverter. So which of the following can be calculated using a Smith chart?
Alpha.
Yeah, the impedance along transmission lines. And what type of coordinate system is used in a Smith chart?
Bravo.
Resistance circles and reactance arcs. And which of the following is often determined using a Smith chart?
Charlie.
Yep, impedance and SWR values in transmission lines, yes. And what are the two families of circles and arcs that make up a Smith chart?
Charlie.
Resistance circles and reactance arcs. All right, here's a pictorial. Take a close look. On the chart shown, what is the name of the large outer circle on which the reactance arcs terminate?
Bravo.
It is the reactance axis. Note they've turned this 90 degrees. I don't like how they've done that, but okay. And on this Smith chart, what is the only straight line?
Delta.
That's where the resistance lives, yes. All right, how is a Smith chart normalized?
Charlie.
Yes, you reassign the prime center's impedance value. No, it's on the chart, it's a 1, but you can make it a 50, and then everything else is multiplied by 50, so yeah. So what third family of circles is often added to a Smith chart during the process of designing impedance matching networks?
Alpha.
Yep, constant SWR circles. I showed you everything inside the 2 to 1 circle there. All right, what do the arcs on a Smith chart represent?
Delta.
Yes, points with constant reactance. Reactance arcs and resistance circles. All right, in what units are the wavelength scales on a Smith chart calibrated?
Bravo.
In fractions of transmission line electrical wavelength, quarter wavelength, half wavelength, eighth of a wavelength. And that, ladies and gentlemen, is time for an intermission and a break. You hung in there. I appreciate it so much. This may be a little hokey, but hopefully it brought it home to you. Let's take our 5-minute break. Come on back, a very short section on antenna design, and then we'll be done. Appreciate you. Let's go for 5 minutes. Well, I want to commend you for hanging in there for those last two sections. That was a lot of material. Easily in an electronics engineering class could have lasted a semester, and we got through it in less than 2 hours. So if you're even more confused than you were before, I apologize, but go back over the material, review, and hopefully you'll have some aha moments and you'll go, oh, that's what he was talking about. But anyway, you'll get it. It'll come anyway. So let's go ahead and get started with the last section, section 9.5, antenna design. Here we're really talking about more antenna modeling and computer modeling. The goal is to predict an antenna's performance before you actually have to build it. And if you can try different options on the computer, well, you can see what the computer modeling says will probably work best. And generally, the models will correspond very well to the practical, the building of the antennas. So software is based on the numerical electromagnetics code, or NEC. One that has been most popular was EasyNEC, still is, by W7EL. This was a paid program up until about 2 years ago, but now it's free, so I'll give you the URL coming up here. It uses something called methods of moments analysis, and it's based on uniform currents in an individual antenna or wire segments. They're modeled along a driven element, for example, in segments, and then combined together. And method of moments is the analysis. So here is the URL for EasyNEC. His last version, he retired and said, okay, I'm going to give it over to the amateur radio community. So you can now download it for free. Now, there is a learning curve, but once you become proficient in it, it's very, very powerful. We mentioned SimSmith and now SimNEC. There's some things you can interchange, I believe, between them as well. So they work together. So this is EasyNEC. Now, if you watch the DX Commander channel, Callum McCormick, I salute you. He tends to use another software called Monogal, which was a joint collaboration between Japanese hams and German hams. This always was free. And so Monogal is another, maybe slightly more easy to use, although still with a learning curve. So EasyNEC and Monogal, and both of them use MOM, method of moments. And here's the analysis of what MOM really means. Just know that it's that segments that are modeled together, they all have the segments of the antenna all have the same current value, and they're added together. And knowing that is the key to understanding method of moments. Now, there are some quirks. Antenna gain, if you do a model, but then you take the model outside the design frequency range, well, then the antenna gain may vary. And if you use less than 10 segments per half wavelength, that's the minimum. And if you use less than that, the software will likely give you the wrong feed point impedance. So that's something that you want to make sure that as you're going through, you use segments of per half wavelength of greater than 10. Well, what can antenna modeling tell you? Well, it can give you standing wave ratio plots, frequency charts of where it'll operate in. Remember the polar plots we looked at last week, the azimuth and the elevation? Well, it can do all of that. And it'll estimate antenna gain and the front to back ratio. And you'll discover that if you use the software and if you optimize for maximum gain, which a lot of hams would like to do, you'll lose front to back ratio. So there's a balancing act that has to go on. So, oh, we're here to questions already. I told you this was a shorter segment. So what type of analysis is commonly used for modeling antennas?
Wrong.
Method of moments, MOM, yes. And what is the principle of methods of moments analysis?
Delta.
Not delta,
Alpha.
alpha. A wire is modeled as a series of segments, that is correct, each having a uniform value of current. They're in
Current, oh,
series. Yeah, so they're gonna have the same current. And what is a disadvantage of decreasing the number of wire segments in an antenna model below 10 segments per half wavelength?
Charlie.
Charlie.
Yeah, that feed point impedance is likely to be off or to be incorrect. And that, ladies and gentlemen, is the end of Chapter 9. You made it. And for many of you, you may have your test coming up this month. Let's see if there's any questions or comments from anyone before we close out of here tonight. I don't hear any. We wore them out. All right, so again, here's the plan. Because of Hurricane Helene, we were delayed 3 weeks. So what we're going to do now is we're going to take a break for Christmas, and we will come back with chapters 8 and 9 and practice tests in January. If you're on our mailing lists, you'll receive emails reminding you about this. Dave, any comments about the upcoming chapter 8?
Yeah, actually 10 is the next one.
Oh, dude, I'm thinking of another.
Yeah, you just finished chapter 9.
Yeah.
So chapter 10 will be our last technical chapter, and then safety will be after that. Well, that's technical too. But I'll send out an email, probably not immediately, something a little bit closer to when the class is going to be, but we'll cover all of chapter 10. And chapter 10 is full of a whole bunch of tidbits, little bits and pieces, but they're very practical pieces in working DX and things of that nature. So we'll see how the signal gets from hither to yon, as they say.
And if you take your test, let us know how you do. You will pass. And even if you pass, you're welcome to come back and join us in January for the presentations there. And then in February, we'll have a technician class if we get enough students, and we'll have a general class. So if you have folks who are looking for that, let them know, and they can get in touch with me by email, and we'll get them in those. So, alrighty. Appreciate you so much. Thank you. Have a very Merry Christmas. Happy holidays. And we will see you next year. Oh,
Yep.
my.
Good night,
73, y'all.
Yep.
Thank you. Happy holidays, 73.
73.
Yep.
Happy holidays.
Merry Christmas.
Merry Christmas, guys. Take
Thanks.
care.
Appreciate it.